Quiz 16.4 investigates our third model of acids and bases, the Lewis theory. And question 1 has to do with the thiocyanate ion, SCN minus. The Lewis structure for thiocyanate looks like this. And in reality, there's resonance between two different forms. There's also a form that looks like this. But if you go based off of our 12-10 rules of putting the negative formal charge on the more electronegative atom, well, nitrogen is more electronegative than sulfur. So we'll just kind of assume that this is the only valid structure. And thiocyanate can act as a Bronsted-Lowry base by accepting a hydrogen, but it can also act as a Lewis base. And remember, a Lewis base is an electron donor. A Lewis acid is an electron acceptor. It's kind of like the mirror image of the Bronsted-Lowry definition, where an acid is a hydrogen donor and a base is a hydrogen acceptor. For Lewis theory, we focus on the electrons, and they take kind of opposite, or you could say complementary roles. So the Lewis base is an electron donor. Well, where might this ion donate electrons in order to form a new coordinate bond and a Lewis adduct? Well, there are a lone pair of electrons right there, and there are also a lone pair of electrons right there. And the reality is the thiocyanate ion can form bonds on either end. If it bonds through the sulfur, then we call it thiocyanate. If it bonds through the nitrogen, we call it isothiocyanate, just to distinguish between the two. But it's capable of doing both. Okay, iron 3 will form a Lewis adduct with a single SCN ion. Identify which reaction partner is the Lewis adduct and which one is the Lewis base. So we'll put the Fe3+ ion here, and we'll build on this as we advance through the questions on this quiz. But we already kind of said that thiocyanate would act as a Lewis base, so we can go ahead and put base there with some confidence. But how do we really know? Well, the iron doesn't have any lone pairs to give. It's a cation. It's not going to be giving up any more electrons than it already has. It's already in a 3+ state. Metal cations act as Lewis acids. So there we are. That's the acid and the base. What's going to be the molecular formula for the product? Well, it will be FeSCN, and the overall charge here will be only 2+ instead of 3+. You know that because it says it will form the adduct with a single thiocyanate ion. Lastly, let's draw a Lewis structure. Well, what's going to happen is that this sulfur lone pair is going to go and form a new bond with the iron. So we'll have iron with a single bond to the sulfur. And then there's no way you could have predicted this, but it's going to sort of, let's see, what are we going to do? We're going to move this lone pair of electrons right there, and this right there, and this right there. There's going to be a bit of a shifting of electrons. What it really amounts to is that the bond is formed like with that other alternative Lewis structure. So you might not have predicted this, but it'll look like this. When thiocyanate forms Lewis adducts, it will tend to switch to this form of the resonance structures where we've got a single bond. Okay, so there is the Lewis structure for the Lewis adduct. Oops, I haven't been scrolling down, sorry. Just so you see the molecular formula for the Lewis adduct. and then draw a Lewis structure for the Lewis adduct. And the last thing we want to say is indicate where is the coordinate covalent bond. Well, it's this one. This is the bond that was formed by 2 electrons from one bonding partner. A coordination bond is one where one bonding partner provides both electrons, instead of a regular covalent bond where each partner provides a single electron to the bond. So here it is. Oh, excuse me. I've got a lot of chalk dust in my nose. All right. Moving on, which of these following is incapable of acting as a Lewis base? Now, some of them are more commonly seen acting as Lewis bases. The only real clue you have is that a Lewis base is an electron donor. And so, a very minimum, in order to act as a Lewis base, a compound or ion must have free electron pairs. So we'll draw Lewis structures, CH, H, double bond O with lone pairs. That is the formaldehyde molecule. Here are lone pairs. So this could be a Lewis base. It could. CH4 looks like this. No lone pairs at all. So this is one which could not act as a Lewis base. It's incapable. What about N2O? We'll have a Lewis structure that looks like this. Well, N2O, you could imagine it acting as a Lewis base on either side there. Cyanide ion. Again, we've got lone pairs on either side. This could act as a Lewis base. And finally, carbon dioxide. Here's lone pairs all over the place. It could at least conceivably act as a Lewis base. So that makes methane, CH4, is the only compound given here that is incapable of acting as a Lewis base. But we're going to see that the carbon dioxide, even though it can act as a Lewis base, we'll see it acting in a different way in just a moment here. Okay, so question 6, we've got this reaction that carbon dioxide gas can react with water. Once it has dissolved in the water and become aqueous carbon dioxide, then it will react with the water to form carbonic acid. And this is a really important equilibrium. It's an equilibrium that happens in our bodies. Of course, we're generating carbon dioxide. We exhale a certain amount of it with every breath. And the pH of our blood is at least in part regulated by this equilibrium between carbon dioxide gas and carbonic acid. And so we want to, this is a Lewis acid-base reaction. And we want to identify which reactant is the Lewis acid and which is the Lewis base. Well, in order to do that, let's draw Lewis structures of our reactants and of our product. So let's see, O, O, H. There we go. That is the structure for carbonic acid. And looking at that, what is a newly formed bond, and what are what's a good way to sort of recognize where that new Lewis adduct coordination bond has formed? Well, we can count the number of carbon-oxygen bonds. We've got carbon bonded to all 3 oxygens in the carbonic acid. And carbon doesn't have any electrons to give, so it seems really plausible now that the water is actually donating 2 electrons to form a new carbon-oxygen bond. And then there actually are some rearrangements. You know, one of these electrons is going to go on one of the oxygens, so that we have 2 single bonded oxygens, and then one of these hydrogens is going to jump over to that other oxygen. So really, we should say this is a multi-step process. So we'll have a couple of arrows. Those rearrangements are not crucial to our definition of a Lewis acid and a Lewis base. The key step is that a new carbon-oxygen bond is formed, making use of the electrons that are on the water, which makes water our Lewis base and carbon dioxide our Lewis acid. If that seems strange, because like I said, there are lone pairs all over on the carbon dioxide, well, it's an acid through its carbon atom. The carbon atom has a lot of bonds to oxygens. That's a really polar bond. Carbon-oxygen bonds are pulling electron density away from the carbon, and so carbon will readily accept a new electron pair in a Lewis adduct because it has a low electron density around it. And it all does make sense once you gain a little bit more intuition about electron density around atoms and how that's going to affect its reactivity. So anyway, I think this is a really interesting case, and of course it's relevant to our own biochemistry, so I was happy to put it in this quiz.